universe. And general relativity, unless you make further assumptions, predict singularities at the center of black holes, but also at the origin of this evolution. Okay? So we don't know from the theory what is going on at the singularities. And this is one of the challenges that people try to address with quantum gravity. The other point is that the matter side of the equation, the matter building blocks, is also incomplete.
Special colloquium.
And one way of seeing this incompletion is if you look at the running of couplings, the way that couplings evolve with energy scale. Well, in this picture here, it's around what we call Planck scale, 10 to the 19 GeV, because we believe that something else is missing here. But if we just try to extrapolate, in particular, this G1 coupling, which is related to the hypercharged sector of standard model. If you extrapolate this, you get a Landau pole, which basically means that at very high energies, the theory breaks down. This is, of course, a perturbative result, so this could be just an extrapolation of perturbative methods, but we also have indications that this is true beyond perturbation theory.
Let's
for this kind of models of quantum field theories
of black holes in a snapshot.
So
all started with Einstein in 1915, when
the point of view that I'm taking in this colloquium, in this presentation, is that something is missing with this description of fundamental physics, and that what is missing is the quantum nature of gravity.
Excellent.
So the idea is that if we add the quantum nature of gravity as the missing ingredient, we can solve this kind of problems that appears both on the gravity side, in the macroscopic side, in the description of microscopic objects such as black holes, but also the evolution of the universe.
Solution for the line element and for the
it can also solve the problems on the matter side. For example, maybe gravity can resolve this issue with diverging couplings on standard.
1931.
Okay, this is, I just to emphasize that this is just a point of view. It's a possible point of view. So far, to my knowledge, there is no
maximum limit
that gravity must be quantized. But this is a point of view that we like to explore and see its consequences. We know that something is missing, and then the idea is what is missing. And one of the possibilities is that we need to account for gravity. We need to treat gravity as a quantum theory as well. Okay?
Landau in 32 postulated.
Why do we expect quantum gravity to be relevant? And this is related to one of the challenges of quantum gravity.
Center of stars will turn.
One way of seeing this is by this kind of Brownstein field. And the different corners here correspond to different regions where different phenomena are relevant. So, for example, this corner here, where velocities are close to the light velocity, we know that we need to describe things in terms of special relativity. In this corner here, where things are small, we know that h bar is relevant. We know that we need to describe things in terms of quantum mechanics. If we put together these two corners, we get to quantum field theory. So adding quantum effects with special relativity effects. And if you go to a region where gravity is important, so where the Newton coupling or the Newton constant is important to describe physical phenomena. And if you go in the direction of adding quantum effects and special relativity effects, we get to what we call quantum gravity.
Said that
so at this corner here, the quantum gravity corner, we can estimate some quantities. We can estimate some length scale, we can estimate the mass scale, and we can estimate some energy scale. These are the things that we call.
He never was very much interested in stars.
These are the things that we call length, Planck mass, and Planck energy. And in particular, let me focus here on the Planck length. So the Planck length is of order 10 to the minus 35 meters. And just recall that the size of the upper bound on the size of the electron is around 10 to the minus 18 meters. So very far away from here. If you want, you can look at things in terms of Planck energy. So Planck energy is of order 10 to the 19 GeV. And if you compare this with electroweak energy scale, this is the scale that we can use that we can access with large colliders. This is of order 10 to the 2 GeV. We see here that the ratio between the energy scale of electroweak interaction divided by Planck energy is of order 10 to the minus 70. So the conclusion from here is that we can expect that quantum gravity effects that are important around the Planck scale is highly suppressed around electroweak scale. In other words, highly suppressed in scales that we can probe with particle accelerators. Even the,
black hole
modern particle accelerators, and as Philip was telling us in his talk earlier, if you extrapolate the evolution of technology on colliders, on energies that we can access, I think the estimative was that we would be able to construct such an accelerator in, I don't know, I think it was 300 years from now, right?
He was a nuclear physicist.
Yeah. So around 300 years from now. So we are very far away from that. And that's why we believe that direct observations of quantum gravity are still a long way out.
So you want to understand the study of gravitational collapse objects.
Difficulty or this challenge to probe quantum gravity directly. Let's try to see what happens on the theoretical side. Let's try to see how we can quantize gravity. And one thing that we can try to do is to copy what we do with other fields in nature. We know how to deal with quantum field theory from a canonical formalism, also from a path integral formalism, and we can try to apply this formalism, these two different formalisms to gravity. If you follow the canonical formalism, then essentially what you need to do is to deal with commutation relations between the metric and the corresponding conjugated momentum. And this is challenging because you have very non-trivial Hamiltonian constraints, and they also lead to the problem of time. And one of the issues with this version, or one of the challenges of this version, is that you are generically breaking manifest covariance in this way. I'm not saying it's impossible, it's just a bit difficult. This part is also difficult, but I prefer this one, so I would say that this one is more difficult, at least for me.
But finally, in 1960, people understood what the solution was.
Yeah, it's because you have to define a time-like surface, right? You are imposing equal time commutation relations.
Not in one coordinate system, in several coordinate systems.
Well, my favorite way is the path integral formalism.
Also in a complicated way.
And what we would like to do here is to integrate over all possible geometries, so integrate over all possible metrics. This is also challenging.
And then in 63.
What we can do in practice, at least at some level, is to integrate over metric fluctuations. And that's what people usually call the graviton. If you quantize this metric fluctuation, you have what people call the graviton. But this is also not perfect. This also, we have to deal with the problem of defining path integrals. We also break some form of invariance, in this case here, manifest backgrounds invariance. But let's try to go ahead and see what we can do about this problem. Actually try to do that. And if you just apply standard QFT methods, so for example, in the 60s, Feynman and De Witt, they used this idea of covariant formulation based on fluctuations around some particular backgrounds in order to compute three-level amplitudes in a KFT style, and they are able to recover some of the classical results from there. So, for example, you can recover the Newtonian potential from amplitudes. I don't know if they did this at that time, but you can also recover, for example, light bending from KFT amplitudes, three-level amplitudes in this way. But the problem at that point was that there was some apparent violations of unity. Later, Tuft and Veltman, they tried to go beyond three-level amplitudes, and they did the first computation of one-loop divergences in quantum gravity, and they found cancellation of one-loop divergences. And I need to tell that at this point was already expected that gravity would be a non-renormalizable theory. But they found this cancellation of offshore divergences. So there was some hope at that point that
it was far away.
There is some miracle cancellation of divergences and things are actually fine, at least onshore. But that's not true. So during the 80s, Gorov and Sainotti did a very complicated calculation and looked at two-loop divergences in quantum gravity, and they found that there are terms that are divergent but do not vanish on shell. So the conclusion here is that quantum gravity is indeed non-renormalized. If you try to apply standard KFT methods for gravity, you get a non-renormalizable theory, which at the end of the day essentially means that the theory is not predictive at the fundamental level.
Importance to black hole theory and black hole developments.
This means that we need to change something if we want to quantize gravity. One way is to give up on UV completion. So let's say you don't care about extending the theory to arbitrarily high energies. Let's try to extend this to up to a given energy that defines a cutoff in the theory. And that's the effective field theory formalism. So the idea here is that you can write an expansion,
then the formation of singularity will
the dynamics
for sure
in powers in some way respecting some rule of power counting.
Probable.
And within this effective field theory problem, if you have energy scales, if you are looking at processes that are characterized by energy scales smaller than the Planck mass, then these extra terms beyond the rest, so this is essentially the general relativity part of the expansion, and then you have a bunch of other things with unknown coefficients that can be, essentially parameterized deviations from general relativity. These extra contributions here, they are suppressed by powers of energy scale divided by the Planck.
Out from
and this is actually true to all orders in loop expansion.
Spherical light rays
this is actually
inwards.
A very good way of computing quantum corrections, because this suppression here is of order 10 to the minus 17 because of the relation between electric scale and Planck mass. So, of course, now I'm just using
if you have a very strong gravitation
equal 1, so light velocity equal 1, so mass is equal energy in this
you
context.
send light rays out.
So this is a very tiny number. So this actually defines, as long as you stay in this regime, this actually defines a very good perturbation theory. Actually better than any other perturbation theory that we have around.
Is a trapped surface.
Describing fundamental interactions. So for example, if we are around the electric scale. And we can use this, for example, to compute quantum corrections to the Newtonian potential. So this is actually the quantum correction. This is a post-Newtonian correction. This comes from loop expansion, but this is actually a classical effect. Post-Newtonian classical effect. This was the first, so this gives the first quantum correction in this,
then they extended the
effective field theory framework of quantum correction. And well, I think it's fair to say that this is basically the only solid result that exists in quantum gravity, or one of the only solid results that exist in quantum gravity. And Sorry?
And they invented the conformal structure.
No, the number has been disputed and so on, but well, assuming that people now understand the number, that's a good point. It took a while until people get the right number. I think I have the right number here. But yeah, so but my point here was, this is a result that any theory of any UV complete theory of quantum gravity should recover in some way at intermediary scales.
It was interpreted.
So the conclusion here is that we do have a quantum theory, a theory of quantum gravity. The problem is that it's not UV complete, and we are ambitious. We want more than that. We want to describe nature and its most fundamental. The second term is it's a post-Newtonian term. I think you can get this from GR directly.
When the Nobel was attributed to Hirsch, it was a cry of people saying that she should have got the Nobel as well, and it was a shame that the Nobel Committee.
Why?
And so on.
I don't know if there is a conceptual reason for that, or if it just come out from the calculation.
Commit the same mistake.
I don't know if there is some reason for that.
Binary pulse or gravitational wave radiation.
Well, one important thing here is that this is very small compared to this in scales where we can measure something.
Hulse. Hulse and Taylor. So Hulse was already.
If you want to describe quantum gravity in a fundamental way, we need to change some paradigm. So this means that we need to.
In 68.
Come on, every time that I have some fun image.
That were totally gravitational collapse.
This means that we need to think. So we need to change something. That's what we understand. So either we can start from different classical dynamics, or we can use some new symmetry principle. We can try to quantize different degrees of freedom. We can try to use space-time discreteness in our favor. I mean, to postulate that space-time is discrete and use this in our favor. We can try to use non-perturbative methods instead of standard perturbative PFT, for example.
It's a very long name. We have to change it. We have to find.
There are two candidates for this that are very popular.
Why not
and loop quantum gravity? And just now I realized that it's fun that string theories also comes with this.
From then on.
Yeah, this is loop quantum gravity.
Black holes.
These are the very popular ones. So if you go to the internet and if you search for quantum gravity, these are the first ones that you're going to find. In string theories, particles are actually composed by something else, but they are composed by vibrating modes of fundamental strings. Because of this non-local character of strings, basically you don't have any more point-like interactions. This is the way that they deal with ultraviolet divergences. And one of the nice things about string theory is that this is a unification theory. So the idea is that the graviton, so the particle that mediates gravity, arises as a string excitation, but also other particles arises as strings excitations. So that's a heavy candidate for unification, unified.
What is hidden behind that?
The problem is that there's several undetected stuff. So
and this paper that we wrote,
the modern versions of string theories are based on supersymmetries, and this was never detected. This also requires extra dimensions for self-consistency. This was also never detected. It's also unclear whether you can recover the standard model of particle physics from string theory.
Totally gravitational.
Quantum gravity was born from canonical quantization.
All galaxies.
So people try to use different dynamical variables to deal with the constraints on canonical quantization of gravity.
So
in a way that you can introduce volume and area operators in the same way that we introduce position operator. in quantum mechanics. Here you have
Penrose process,
volume operator and area operator.
extract.
And one of the things that follows from this quantization is that you have discrete spectra for these quantities.
Process.
So you have some notion of discrete space-time in this way.
Everything's
This has been applied to cosmology and black holes, but it also has some downsides.
from the Penrose process.
It's unclear how to recover the continuum limit. It's unclear if we can add standard model to this picture, and so on. So at the moment, we don't have any, the main candidates, the two popular kids in school, they still have some issues that we need to understand.
The angular momentum could be active.
There are actually other kids in school. We hear more about the first two ones, but there are many alternatives to quantum gravity. Nowadays, there are also people trying to connect these alternatives. If you want to learn more about this approach, for example, you can look at this book edited by Daniele Orici on approach to quantum gravity. This already has, I don't know, it's around 15 years old, I think, and there is a more recent handbook of quantum gravity that explore. Well, I think it basically explore all the
area of
approaches that have been,
the area of the black hole cannot
at least that
decrease.
has more than one people trying to do.
Two black holes together increases. Now this
It's not a handbook. I mean, it's the usual thing that we call handbook in science, right? As I said before, there are some people trying to unify this approach, so to gather the kids. And this is the International Society for Quantum Gravity. Antonio in there is one of the founders. Satish over there is also very active on this. And they're trying to put together the different communities of quantum gravity.
In terms of the black hole that is not seen, of course. But
the idea is that we should talk to each other and try to solve common problems.
Of the binary candidate to the central mass and
now I'm going to move to the parts that I'm very suspicious to talk about because, well, this is my favorite way of addressing the problem. Which is the renormalization group approach to quantum gravity. In particular, what we call asymptotic safety. The idea of asymptotic safety, or the main idea of asymptotic safety, is that we go beyond perturbation theory. As we try to get rid of the lack of predictivity of non-renormalizable theories. How do we do that? We assume that higher order terms that are generated in a non-renormalizable theory is actually part of our theory. And we conjecture that there is a new symmetry principle that is realized in gravity, which should be responsible to restore predictivity of the theory, despite of being perturbatively non-renormalizable. And this principle is scale symmetry, or sorry, quantum scale symmetry. Scale symmetry is this kind of self-similar behavior that we obtain by zooming or zooming out something. And the notion of quantum scale symmetry is that this is not a symmetry of the classical world, but only of the quantum world. So you're starting from a classical space-time, things are not scale invariant, you zoom in, you see different structures, and at some point you start to zoom in even more, and then you get to the quantum regime, and you have this emergent self-similar behavior popping.
The area.
Yep.
Never decreases.
There are some associations between quantum scale symmetry and minimal length, but it don't have a fundamental.
What was the right connection? If it was.
There's a difference between what we call classical scale symmetry and quantum scale symmetry. Quantum scale symmetry has to do with the behavior of dimensionless couplings.
When you have two equations.
Yeah, but it's indeed it's hard to consider minimal length of this. But I just want to mention that there are some works
I met him several times, one of the times
where they explore this, but I don't remember the details.
I was not
Okay,
the
so
first.
that's not the common view.
I asked him how you hit on the typical entropy, and he said, "Well, it appeared to me."
The idea is that, so I mentioned that this is a renormalization group approach. And the idea is that this is a renormalization group approach because what we call quantum scale symmetry is related to fixed
connected
points
with
of the
this,
randomization.
appeared a formula called
We
smart
do have
mass
fixed points in
formula for
other
black holes.
interactions. So for example, if you look at the
And,
strong interaction
Smart,
of the standard model,
was a
you have this
physicist,
kind
I
of
think he was
asymptotically free behavior for the
was
strong
still the
coupling,
beginner, but I'm not
for the
sure.
QCD gauge coupling.
And Smart
This basically means that the
found a
couplings
formula that connected the angular
got
momentum.
you, I mean, if you
concentration and
increase the
wealth
energy
of the
scale,
black hole,
then you reach
which
fixed point
look
at
like,
vanishing coupling, and then once you get
Euler
there, you
formula
stays
for
there.
thermodynamics.
And the idea of
And it's now
asymptotic
called
safety is to
Smart.
generalize this picture.
And at the same
Actually,
time,
you'd
I
want to
think
do
this
this
is
in a
very
version. Instead of going to a vanishing
I'm going to talk
coupling,
about that
you
later.
stays
So
at a constant value for dimensionless couplings.
the mechanics of black hole,
And the fixed point regime essentially corresponds to the scaling variant regime of the theory.
now we know
So
you
here we
know
can
there
see
were
that
four laws
in this region here for
of
small values of
thermodynamics.
energy,
and
things are
now
varying, so
they can
we are
stand
not in a
the
scaling
scale
variant
of black
regime
hole
here,
entropy.
but then we
So
tend to a
things
constant
started
value, and then we enter a scaling variant regime.
to join together.
Okay? Well,
74,
one of my favorite
think
pictures in
shows
asymptotic safety is this one.
remarkable paper.
I have been
think
using this
maybe
since
the
my
most important
PhD
discovery in
thesis
the second half of
and recycling this. And
that,
this is the notion of what we
what
call
is called
critical
now
surface.
Hawking
You can define a space
so
with
black
all
hole
possible couplings